Okay. So we didn't start this practice problem at all?
No.
Did we make a prediction about where the force would be greater?
No.
No? Gosh, we didn't do anything. Okay, so let's pretend, imagine that we're swinging this thing, this mass at the end of our string. Where do you think the tension is going to be at the greatest? Why at the bottom, Luke?
Because gravity.
For sure. So if we kind of think about our forces, like you just said, the tension is acting upwards here, whereas the gravity is pulling down. Force of gravity. And then at the top of the circle, the tension would be acting downwards, and then the gravitational force would also be downwards. So it would make more sense for our tension to be really strong at the bottom. That's kind of in the back of our mind. We're keeping that as a way to check ourselves. So then let's do that. At the top, we would have centripetal force equals tension plus Fg, which means that the tension is equal to centripetal force minus Fg. So if I just subtract Fg across and then rewrite my equation, my tension will be found by doing the centripetal force minus Fg. Now, of course, we need to find these things. How do I find Fg? Yeah, it's just mg. Did they give me a mass? Show did 1.7 kilograms, so Fg would be 1.7 times 10, which is 17 newtons. So that one's easy. What about centripetal force? Remember on our formula chart that's equal to
Ft. Or sorry, tension. Oh, sorry, mg. Wait, hold on.
Let's have a hand up. Somebody with an equation I thought we could use. Steven, did you have it?
Yeah, v squared times divided by r.
Yeah, we could do mv squared over r. Or remember the other way is the long one, the m 4 pi squared r over t squared. So let's think about which one makes more sense to use in this equation, or in this scenario, I guess. They give us the time for one revolution is 1.1 seconds. And they tell us the radius of the circle is 0.6 meters. So what do we think?
Probably the n4 pi squared.
Yeah, I think this one's going to be more direct, right? Because they give us the radius, we have that. The mass is given, the time is given. I think it would make a lot of sense to do that. So let's plug in our values. We'd have 1.7 kilograms times 4 pi. That's 4 pi squared times the radius, 0.6 meters, all over the period squared, 1.1 seconds.
I was so tempted to say 2a because I was thinking of the quadratic formula.
2a. Yeah, I do that. I do that same thing. Yes, you have good math teachers if you remember these things. So that means that the centripetal force is, you can check the number if you want, should be about 33.3 newtons. Somewhere around that. Okay, so if we think about this, Fg is 17, Fc is 33.3, we can come back up here and we can solve. We can do 33.3 newtons minus 17 newtons, which gives us about 17 newtons. Then at the bottom,
16.66.
right, we can round that up to 17 for sure. Now at the bottom, what changes? Yeah, I'm gonna, well,
Of tension.
writing my thing is gonna be tension minus Fg, but if we're solving for tension, y'all are right. It is gonna be tension is equal to Fc plus Fg. Which just mathematically being logical, of course it's gonna be bigger if we're adding two things instead of subtracting a thing and a thing. And so that would make sense then for us to do 33.3 plus the gravitational force, which was 17 newtons, which gives me a tension at the bottom of my string of 50 newtons. Now, here's a question. Why does it matter? Looking for a hand. Why does it matter that the tension is bigger at the bottom versus at the top?
Doesn't that mean it's not uniform circular motion anymore?
Ooh, does this mean we're not in uniform circular motion? Adam, you say no, why not?
The tension has to be greater to keep the flow good, to keep the object going in a uniform.
That's right. The tension has to be greater to keep it in uniform circular motion. If we didn't have a greater tension at the bottom, then gravity would take things and kind of get them out of whack, and we would start accelerating one way or the other. But because we have a constant acceleration towards the center of the circle of FC, we must have a greater tension at different points, because these 2 points versus this, where they're working together, it all has to have the same acceleration. Otherwise, you would be right. I wouldn't be in uniform circular motion. Stephen?
Is that why it kind of forms an ellipsis if he's swinging up and down?
If you're saying like in real life?
Yeah.
Yes. And like we're going to get into Kepler's laws of ellipses, and that all orbits are not circular. They're all ellipses. It's exactly right. Now, the other thing we can think about, we can take this thought experiment even one more step, and I need to stand up and move for this. So as I'm swinging, as I start to go slower and slower until I'm starting to get to a minimum velocity to maintain uniform circular motion, what happens to my string as I start to hit that minimum speed? I lose tension. It starts to go to 0. So that's the next part here. It says, suppose that the mass is swung with just enough speed to keep it moving the circular path. The tension at that exact point, gosh, that's so loud. I got to turn that down. The tension at that point would be what value? It would be 0. The tension would be equal to 0 at that point. Meaning if I go any slower, my string is going to stop. It's going to fall. And we would say it's like weightless at that point. Have you ever felt this before? Have you ever gone really fast in a car over a hill? It's the same thing. If you're in that case, you'd be going into maximum speed. And then if you go any faster than that, what happens to you? Or maybe even the car?
You go up.
It goes up. It accelerates vertically up off the ground, and you go through a sweet jump in your 1996 Nissan Maxima up Pasadena. You know the street over here by the apartments? It's kind of an uphill coming towards Ryder, and then at the very top, it's a little hump. You can do this really nicely at about 50 to 60 miles per hour. So not speaking from experience, just an example. Just random example, just making things up.
Yeah.
Just kidding. Great thing to do. And so the big idea here is it's just gravity.
Is that why in a parabola, when you have the peak, the velocity is 0?
That's kind of a good way to think about it. Yeah, at that high point, tangent line would be velocity equal to 0. Yeah, you can think about that.
So then the tension would be 0 at that point as well.
The tension is 0 at that point if we're going at a minimum speed. That's a key. So here, the idea of a minimum speed means that FC is equal to FG. And we're going to model this in just a second with a bucket of water.
Oh,
So
is
if
this
we
what
set
the book was talking about?
Hmm?
Is this what the book was talking about when it said something about critical velocity?
Yes. Yes, most likely.
Big brain. Thank you.
This would be mv squared over r equals mg. What can we do with the masses then? Yeah, we
Cancel them.
And so we would have v is equal to the square root of g times r. So for example, if I have like a bucket of water and I spin it with just the right speed, I can get the water to stay in the bucket without it falling out. Right? Shall we? I have a bucket here. Can you get some more?
But then why is the tension 0 if there's gravity involved?
Hold on, I need a bucket of water. Gotta get you on the splash zone here. You don't want to live life on the edge? Okay, before I swing my bucket, Bargaby, what's your question? You said about
So why exactly is the tension 0 at that point if gravity is still present?
Gravity is the only thing that's present. Remember, let me go back up. Oh, it's not going to be there. That's awkward. Let me go to the filled-in version of the note so I can reference this.
So like it's kind of like when you're like, if you were to swing the bucket, you wouldn't be pulling down. You wouldn't have to pull down on the bucket.
Exactly.
If you're going at a medium speed because it's got enough
Momentum.
to get
Momentum, you can think about it as inertia, either one of those. Yeah, pretty much when I look at the more centripetal nodes here, zoom in, there was tension and there was FG at the top. There is tension and FG at the bottom. But at the top, if I'm going at just the minimum speed where only gravity is acting, then tension goes to 0. That's what we're saying here.
kind of like you're just kind of swinging around letting it hit and it's swinging.
Right. So example here, people at home, I'm not sure if y'all can see this very well. Let me try to get you on screen.
So in this case, would that mean that Fg is the centripetal force?
Yes, that means FG is the centripetal force.
Okay.
So like when I swing my bucket here in a circle, lead on. When I swing, right, the water stays in the bucket, and I can slow down. You can start to see it come out if I start going too slow. But if I'm right about at that speed, can you hear it? You can hear it like trying to come off of the bottom of the bucket. And then obviously if you go really fast, then it just locked in there. You know, it's not going anywhere. It'll like go.
I'm just
No. So, and I could add even more water, right? The mass doesn't matter, as we just proved. The mass cancels out. So it's the same thing. The only thing that changes it, what changes the speed I have to maintain? Why do I have to go faster right here? Smaller circle, exactly. As the radius goes down, I have to apply greater force. Exactly. So, kind of a cool thing. So the big take-home message, you can flip over to the backside. Right here, this is what we're going to fill in. If the velocity of the object is constant, then that means that the velocity only depends on the radius and the period, which means centripetal force is equal to force gravitational. Fc is equal to Fg. Sorry, this is on the next page, that page 3, people in the room. So this, you can kind of think of it as like a shortcut equation. The V equals the square root of GR. It's only when you're doing something with like the minimum speed. Or sometimes the maximum speed, because it's minimum if you're doing tension. Because once you go below the minimum, your tension becomes 0 and then it just goes slack. If it's a maximum, that'd be like riding a motorcycle over a hill. If you had the radius of curvature of the hill, you could find the maximum speed you could go in order to just have gravity being the only thing holding you down. Because then instead of tension, what force are you dealing with? I think this was on the reading quiz. It had a question about the car driving over the little hump. It had FG and then what was going out? Normal force. So in the case of going over a hill, the normal force seems bigger, but it's just an apparent force.
Mr. Henderson, is the velocity constant when we're going horizontally and spinning?
I guess really this should say speed, but in our definition of 2 pi r over t being the velocity, nothing's changing because the radius and the period are not changing.
Okay.
It's apparently greater at the bottom
When you're swinging a bucket,
or the car and
well, and a car in a hill, yes. Sorry, did I say greater?
I think he
Over
said
the
like
hill? I meant
over
less.
normal.
Yeah, you'll feel like you're rising, like your stomach's
Okay.
fluttering. So
So
it'll feel like
over-
less.
FG would be greater.
Correct.
Okay.
Yes. Just like in an elevator, when you're shooting up at the beginning, your normal force feels greater. That's why you feel heavier. Yep, I said that backwards. Okay, let's take a brain break and then we'll go on to the next thing. How many of you have directed music before? Anyone? No. This is the choir director brain break. So here's how it works. You're going to take your arms and put them out in front of you and about 12 inches apart like this. And then you're going to create a figure 8 in front of you. So like this. You're going to do it in a second and stand up. Then you're going to do the same thing with the left hand at the same time. So like this. Choir director.
Are we casting a spell?
Are you what?
Are we casting a spell? Are we summoning a demon or something?
I hope not. Goodness. But then here's where it gets tricky. Once you've mastered that, you can try doing it opposite. So like your right hand's going to go up and around, and the left hand's going to go under and up. So like opposite. You got to stand up to do it. Stand up and try. People at home, stand up. Get out of your comfort zone. So start just normal. And then you can do both at the same time normal. That's pretty easy. Then when you try the opposite, it gets really difficult. So just keep that kind of middle central point on your focus, and then you can kind of do it. Your eyes kind of go crossed a little bit. It's okay. It's physically painful to do that. Whew, it's tiring. Once you're sufficiently frustrated, you can sit down. All right, good job. Y'all are music directors. All right, let's finish this out. Let's do our last example, and then we'll be donezo. So we talked the other day about banked curves and unbanked curves, meaning like flat road. In reality, though, most roads have a little bit of a slant to them, like this. So what are we going to have to think about in terms of the slant?
Angle trigonometry.
Yeah, he's right. We're going to have to do a little bit of trigonometry, a little bit of angle action. So let's do it together. It'll be easy. Thinking about the forces. Austin, what would be the free body diagram for this situation? Can you tell me what forces and where?
Like just okay. So normal force is like its directions are flipped this way,
Okay.
up away from the ramp.
Okay, good. Away from the ramp like this.
Yes.
What else?
Remember correctly, force of gravity is down, not against the ramp, against the floor.
Very good. Against the floor. So straight down is exactly correct. Well done, Austin. Anything else?
Friction?
Frictionless.
Oh,
Aha!
sorry.
Bargaby fell for my trap. Good, Austin. This is a frictionless surface. So that's it. We're done. He's done. The only forces that act on a frictionless corner, as you're going through a highway, let's imagine that we're driving during the ice apocalypse of 2021, after the year of mask. It'll live in legend, I'm sure, for years. If you went through a pure ice highway curve like this, which you could have done, I did it, but I'm in the Subaru, you know. But anyways, if you did that with no friction, what are the only two forces acting?
Gravity and normal force.
Gravitational force and normal force. But something we should notice is the Fn is larger because it has to both oppose Fg. In other words, it kind of matches Fg. And it accelerates where?
Towards the center of the circle.
Ding, 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 always the answer, always the winner. Accelerates inwards into the circle. Now, if you can't picture the circle, here's what you have to kind of think about. Imagine, I'm looking right now at the booty of the car. So here's my taillights, not butt cheeks. Taillights. Imagine we're looking down on that car as it's going through this curve, as it's turning around a big loop-de-loop thing. Okay, so like put yourself bird's eye view down on the car. It's turning under us. So that normal force, as Austin described it, coming off of the ramp, if we're looking down on the car, and it's actually that normal force would actually point towards the center of the circle of the turn. Does that make sense?
So this is like back view.
So we're looking currently at rear.
Like a racetrack kind of thing.
A racetrack, exactly. NASCAR. Vroom,
So
vroom.
we're still turning. Oh, wait. Is it the whole slope that's turning? Like,
The
what
whole
is
thing
it?
is ramped and turned, yes. If it was three-dimensional, it would be like crazy to draw. I don't know that I could do it. Imagine like I'm like watching the rear view. There's Lightning McQueen going around the curve. But it's curved because then we don't need as much friction, right? In fact, we can do this with no friction if we are not going too fast.
So then Fn is inward towards.
Exactly. It's
Okay,
inward
okay.
towards the center of the circle, even though for us it kind of looks like it's going upwards. It's actually more inwards. Yeah. So FC is the last thing here.
Would
Cool.
it need a minimum speed to keep going to not slide in?
We would certainly in order to keep us up on the track, but that's kind of beyond what we can do. Let's look at an example, and I think it'll help kind of y'all see what we're doing with this. This is our last thing here. We can do the frictionless curve one, or we can do the toy plane. Which one do y'all prefer?
Plane.
Toy plane? Okay, we'll do toy plane. Do it for the children.
It seems more colorful.
It is. It is actually an easier question too. So good choice. It's got more room.
I heard Toyota plane.
Toyota plane. Okay, let me draw a little Yoda on here. Hold on.
Oh, I was thinking you were gonna say like the car, like a Toyota, and then never mind.
Oh, I thought you were talking about Baby Yoda. Never mind.
I was talking about the car, but Baby Yoda is better.
Okay, wonderful.
Yeah, now we can have Yoda join this.
Here's
Wait.
Yoda and a plane.
Yoda
Yeah.
is sponsored by Toyota.
Toyota, sponsored by Toyota. Wow, if Toyota made a toy that was a little Yoda, that would be genius. Okay, I'm gonna contact them after this Google.
Sales and marketing hacks for Toyota.
So what force would be right here on this approximately straight line that I drew? Tension, thank you. So if we draw that tension vector, and then we know there's also a gravitational force vector. So let's add that vector, do a little vector trigonometry, right? What would my resultant vector be right here?
Centripetal force.
Ding, ding, ding. And where does it point?
Inward.
Inward, always towards the center of the circle. How convenient. So it would basically be here in terms of forces. This would be the centripetal force. But again, don't put it on the free body. Just leave it over here on our diagram. Oops, that was supposed to be red. Now, what do we know? We know it's a 0.25 kilogram toy plane. We know it's got a radius of 0.8 meters. We know that it's at a 28-degree angle, so we can add our angle here, theta. It's 28 degrees. So let's solve. What are we going to use if we're using this angle, 28 degrees, and we're looking for centripetal force and Fg?
Sine.
Sine
Oh,
code,
sorry, tan.
we're going to use
I mean, you could use tan, yeah.
tangent of theta would give you Fc over Fg, which means we're going to have mv squared over r over mg.
Can we still cancel out the masses?
Yeah, we can actually. Now, do we know the v though?
No.
We
But
could.
can we replace that or something?
We could replace that with
4 pi.
2 pi r over t
Oh, right. Sorry.
squared over r over g. It's starting to get a little messy. So really, we know that this reduces to 4 pi squared r over t squared over g. Well, I hope this is right. What are we trying to solve?
FC. Oh, never mind.
We want the period of rotation. So what
T.
do I need to get by itself? The big T
The
here, right?
T.
Now let's pause for a minute while people are catching up, I think. The big T, is this tension or is this a different T?
That's the period.
This is the period. This is why physics makes no sense and it's so stupid, right? You know, it's so hard and everyone hates it. There's so many T's. Like there's little T for time. There's big T for period. There's big T for tension. There's big
Physics, we
You-
have an
Sarah.
also T.
regardless though, this is the period. That's what we want. So if we rearrange, we would have G tan of theta equals 4 pi squared r over t squared. Okay, let's get t by itself. So let's do just kind of flippity flip. Multiply both sides by t, divide by g tan of theta.
Square root of 4 pi r
Over g tan of theta.
over,
So
yeah.
we're
I'm
just
trying to do mental math.
square root both sides. So we ultimately, on our calculator, we're going to go to it and do 4 pi squared times the radius, 0.8 meters, all over g, 10, times the tan of 28. That will give me my period.
This is the easier one.
Uh-huh. Well, we kind of did it a hard way, but it ultimately gives you 2.5 seconds. what we could have done, you don't have to write this, but we could have just done centripetal force is equal to, if we just, let's say, isolated this and didn't go down this dark path right here, mv squared over r, if we just found centripetal force, it would be Fg tan of theta. And then we would have got an answer. Centripetal force alone would have been 1.3 newtons. Then all we would have had to done was centripetal force is equal to 4 pi squared r over t squared. Plugged in 1.3 here and then solve for t. So it's functionally the same thing. It just looks neater this way, solving part of the equation and then plugging it in. Because then your t is the square root of m 4 pi squared times r, 0.8 meters, all over fc, which is 1.3. So that might have been the easier way. We tried to do it all in once, which involved a lot of algebra. It was kind of painful. But it gives you the same answer, 2.5 seconds. So what's the take-home message? Yes, Barnaby. What's the take-home message here? Does it matter?
No.
No, it doesn't matter how we do it, as long as we do it. There's many ways to skin a squirrel, as they say, or skin a cat. Okay, if you want a different example, you can go look at that frictionless curve one. You're welcome to look at it, it's online. But what I'm gonna give you for the rest of this period, which is about 15 minutes, is time to practice, because that's the number one thing that helps you be smart. There's online, I posted all of the practice problems in one post to make it easy for those of you who are online right here. Practice UCM and gravitational force. The one you're going to be looking for is 5.1 and 5.2. So 5.1 is posted in PDF and Word format. 5.2 is the one that's a little harder. So on 5.1, let's do the odd problems. So you might want to make a note of this. The odd sheet, 5.1, do the odds. And the sheet that's even, 5.2, let's do the evens. Make it nice and easy.
1 is odd, 2 is even, 5.1 is odd.
Odds, 5.2 evens. And the nice thing about 5.1 and the odds is we already did number 1 in the notes. We did the centripetal acceleration of the moon towards the Earth. So if you don't remember how to do that, you can look back on the page 3 of the first set of notes, and you'll find that worked out for you to get your brain in gear. And yes, you have to look up the radius of the moon and the speed of the moon.
Can we like go over that formula with the M1 and M2 with the little g of 6.67?
We're not doing that yet. That's orbits, that's tomorrow.
Okay.
For this Barnaby, all you would have to do is you would just look at mv squared over r. But really, they just want centripetal acceleration, so you don't even need m. Centripetal acceleration is just v squared over r.
V squared over r.
Yeah. So if you know the speed of the moon and the radius to the moon, or you could also do, remember, your 4 pi squared r over t squared. That's also equal to centripetal acceleration. So if you looked up the period of the moon, which is 27.3 days, and then the radius to the moon, which is a big number that I don't remember, then you solve for the acceleration.
Okay.
Yep.
It's mainly like the units on the equation for tomorrow.
That is mainly just for cancellation on the big G. We'll talk through that tomorrow.
Yeah, I just want to clarify. I think I did those problems wrong because you gave us a worksheet on that, but
I just wanted to expose you to it a little bit. Okay, let me let you start practicing that. If you want to work with people, you can. If you have questions, ask me, and then we'll finish that practice tomorrow. It is not homework tonight. Your only homework is to be prepping for the test next Thursday. Let me stop this.